In this lecture, I'm going to give an example of the Fourier series. So the first thing is you have to draw a picture. I'll do an example of that in class, but it is as simple as drawing a picture, but the picture repeats. So what you need to do is you do one version of the picture from minus pi to pi, and then you repeat it either side, and it repeats and repeats and repeats. And I'll do examples of that in class. So one way to think about functions are they even or are they odd? Why this matters is it simplifies your life. If something is even, it's a sine, it's a cosine. If it's odd, it's sine waves. Even and odd makes life a lot easier. So you have to think a bit about that. So what is an even function? An even function is something that's perfectly mirrored to the left and right. So if we draw a line for the y-axis to the left and right, it's perfectly mirrored. While an odd function, if you draw the y-axis, it's not mirrored. But if you draw a 45-degree line, it is mirrored. And what that means is, if it's negative on one side, it'll be positive on the other, and if it's positive on one side, it'll be negative on the other. So it goes plus minus. So a simple even function is x squared. X squared is perfectly symmetric around 0. When x is 1, x squared is 1. When x is minus 1, x squared is 1. They mirror each other. An odd function is the line. When x is 1, the line is 1. When x is minus 1, the line is minus 1. So when you put in the minus version, it's just minus the positive version. And that's our definitions. Odd functions and even functions. Cosines are even functions because they're perfectly symmetric to the left and right of the midline. Symmetric to the left and right of the midline, while sine waves are odd functions. You see here? That's the plus part, that's the minus part, and that's our midpoint. And they're just the flip of each other. So the sine of pi over 4, the minus that is the sine of minus pi over 4. They're perfectly around 0, and there's plus and there's minus, and they cancel each other out. In the last lecture, I talked about how sine waves are made up of amplitude, frequency, and phase. In Fourier analysis, we simplify to just go amplitude and frequency. Same with cosine, we get rid of the phase, it's just amplitude and frequency. So the Fourier series is a summation of sines and cosines of different frequencies. N is the frequency. So here we have a summation from n is equal to 1 to infinity, n is equal to 1 to infinity. So that means frequency 1, 2, 3, 4, all the way to infinity. And then there's a constant term as well. The function can be divided into these series. Every signal can be written in this form. And what we want to find out is A0, AN, and BN. And to do that, we need to do integration. If we're given some function or some signal, we need to integrate it to find out what A0 is. And then to find out the powers for the different frequency bands, we multiply the signal by cosine, and we integrate between minus pi and pi. So let's take our example of our square wave, which I spoke about in the last lecture. So our square wave can be written as Sx is equal to minus 1. So that's minus 1 from minus pi to 0 and plus 1 from 0 to pi. And it repeats minus 1 plus 1, minus 1 plus 1. Now, on top of my square wave, I plotted a sine wave in red and a cosine in green. And what you see is the sine wave is the one that aligns better. When sine is high, the square wave is high. When sine is low, the square wave is low. It doesn't fit as neatly for the cosine. So immediately go, sine waves seem like a better way of estimating the signal. And we know that to be the case. So we have to integrate this. So how do we integrate something in that form? So here we have something that's broken into two parts. So we break the integration into two parts, from 0 to pi, or from minus pi to 0 is -1. And from 0 to pi, it's +1. That's all times 1 over pi. And we integrate that. The integral of -1 is -x. The integral of 1 is x. So that's from minus. And so that all cancels to give us 0. Now, why is it 0? Because sine wave is minus and then plus, minus and plus. It always cancels. So it always stays. If you actually added the plus minus together, it'll always stay around 0. That's why A0 is 0. Then AN. So here, once again, AN is our function times our cosine x. So our function is minus between minus pi and 0 and plus between 0 and pi. So that's that part and that part added together. And when you integrate cosine, you get sine. So what we have is minus sine nx divided by n. Remember, when it's cos nx, n comes out and is divided by sine nx divided by n from 0 to minus pi, 0 to pi. And if we put in the values, so we put in x is equal to 0, x equal to minus pi, x equal to pi, x equals 0. So the sine of 0 is 0. So they all are 0. Now, what's the sine of pi? Well, sine of n minus pi can be rewritten. That minus can be brought out. So that gives me minus sine n pi plus, and they cancel. But also, the sine of 1 pi is 0. The sine of 2 pi is 0, and so forth. So it all cancels to 0. And why does it all cancel to 0? Because A0 is about cosine wave. So it means there's no cosines involved with this. So now what we have is our square wave, which is -1 plus 1, has no amplitude for A0, no amplitude for AN, but it's the BN, so stuff that matters for the sine wave, the one that we saw aligned the best with it. So we integrate here with respect to sine x. So we multiply -1 times sine x being minus pi and 0. Plus 1 from 0 to pi, so that gives sine x. We integrate that, cos nx divided by n minus cos nx divided by n. And we put in the values. And so what happens here is cos n0 and cos n0, they add together. We need 2 cos n0. We have 2 minus signs. And so now what we find here is this goes to -2 times cos n pi divided by n plus cos n0 divided by n. So we can take the 2 out. And so we have cos n0 minus cos n pi. Now, what is that? Cos n of 0, or cos of 0 is 1. Cos n of pi. Cos n of pi, when n is equal to 1, is -1. So that's 1 minus 1 minus -1. So that's 4 divided by pi. So that's here us letting n is equal to 1 into this format, 4 pi. When n is equal to 2, cos of 2 pi is 1. So that cancels to give us 0. When n is 3, you get -1 again. So we get 4 divided by 3 pi. And it keeps going. When it's odd, you get 4 divided by n pi. So that's 4 divided by pi, 4 divided by 3 pi, 4 divided by 5 pi, 4, and so forth. And for the evens, it's 0. And so now it means that the square wave is made up of odd frequencies of power 4 divided by n pi. So if it's only odd, you can do it like this, but this answer is good enough. This shows me that you know what happened, and you put that back into the main formula to say, that's your Bn. So our square wave can be rewritten as sine waves n divided by pi, 2n to get your odd numbers, 2n minus 1 for each of them. And that gives you your frequencies. And that brings us back to this picture where I showed that adding different sine waves together of different amplitude and different frequencies gives you something that looks like a sine wave. And if you do 100 times, it gets closer and closer. It's not perfect because a square wave is very unnatural. And it's very hard to represent by smoother functions, but it can be. Yeah. Now, another way of thinking about even and odd functions is think about it in terms of art. An even function is like Michelangelo's David, perfectly symmetric on either side. Michelangelo's David, perfectly symmetric along the line. while the odd functions are more like Picassos. All the eyes are on one side and the mouth is on the other. They both are important and they both are beautiful in their own way. So in the odd functions, you know, what odd functions, even functions can only be made from even functions, odd functions can only be made from odd functions. Now, there are many functions that aren't even or odd, but there are some that are, so therefore that's why we start with them. If a function isn't even or odd, it'll have both a's and b's. So to sum up, here is our formula. A0 divided by 2 plus an cos nx plus bn sin nx, where a0, an, and bn are made by integrating. But if it's an even function, bn is 0 because bn is the odd functions. So you calculate a0 and an only. And if it's an odd function, you only need to calculate a bn because a0 and an are 0, just like we did in our square wave example. So in class, we'll do many examples of deriving through doing the pictures, and hopefully it'll become more and more intuitive as we go.